Hey everybody, Newland here. Let's talk about comets for a few minutes and wrap up our discussion of solar system objects. So, when the solar system formed, all the volatile stuff like water and methane and hydrogen and the lighter things were pushed out towards the outer part of the solar system. And out past Neptune, there is a ring of cometary objects, and then even further out is theorized this cloud called the Oort cloud, which we've discussed before. These are objects that are majorly made of ice, meaning that instead of a rocky object with some water in it, these are some watery objects or icy objects with some rocks in them. For the most part, they're made of, as far as we can tell, water ice, even though objects in the Kuiper belt can have different types of ices. Cometary objects, for the most part, we think of the water content in terms of the ice. Here you can see an image of a very eccentric cometary orbit. Let's say it was like, it's supposed to be like Halley's comet, for example. It's just an example, though. Notice that the period of time the comet's close in towards the sun, near the Earth, is a small proportion of its overall orbital period. Remember, an object goes fastest when it's closest to the sun. So that the period of time the comet is close enough to the sun to develop a tail is actually when it's way down over here in this part. So you'll see that the majority of its orbit is actually happening way out here, and that's actually a much longer chunk of time. So it's going fastest here, and this is maybe a few months at a time. There are two parts to the tail of a comet. It's as this object gets close enough to the sun, the ices evaporate, or at least vaporize in some way, sometimes internally, sometimes from the surface, and you end up with this cloud around it, and as the object keeps moving through space, it leaves behind this material. The stuff that is neutral, or the dust tail, is different than the stuff that's ionized, or the ion tail. And the ion tail always follows the solar wind, whereas the dust tail is going to leave behind this curved shape pointing away from the sun at all the points where the dust is leaving the object. But as it continues to move in its orbit, the dust tail is going to look more curved, and the ion tail will always look straighter. Sometimes comets don't end up with both tails discernible. Sometimes it's all kind of intermixed. It depends on the size of the comet, how close to the sun it gets. In this image you see the inset B. This is a very bright comet, and its dust tail and ion tail are clearly split into these different parts. The very central part of it, the actual ice ball itself, now every comet is just this little ice ball, but once it develops a tail, that this area around it with the gas, the vapors that have erupted, can be thought of as these different parts. There's a coma towards the center bit there. It's kind of like a teardrop shape, and then there's the tail. But there's also sort of a vague cloud around it that's known as the hydrogen envelope. You can tell that the sun is that direction, the solar wind pulls the ionized stuff straight back, and the dust tail is kind of left behind as it goes. So here's a really good example of what I mean. There's an ion tail. You can even tell it's giving off its own light as the excitation in this chunk of gas are causing it to glow on its own, whereas the dust tail just kind of looks like this white puffy thing. And there's another really good example. Actually, I think this is a zoomed in version of that. And here you can see that the tail can be really, really long. The dust tail is always curved, or usually curved, or weirdly shaped like this, whereas the ion tail is always going to end up looking straight. By the way, being able to see a comet in the sky like this is fairly rare. There's a reason why they have such an impact throughout human history on people's perception of what they might mean. Is it an omen? Is it something scary? Because seeing them in the sky, especially in modern times where we have so much light pollution, is pretty rare. There was one visible during the summer of 2020, but it wasn't visible without a pair of binoculars. The telescope made it even easier to see. So I think I zipped through there. So I mentioned this already a little bit, but the speed at which a comet passes the sun is always going to be faster than when it's farthest away. So this period where the comet seems to develop a tail, both an ion and dust tail, that's always pointing away from the sun, it's going to zip through that part of its orbit. So the confusing thing is, as the comet is turning, its dust tail ends up in this arc because it's, following an elliptical path, whereas the ion tail is always pointing away from the sun. A lot of people think the comet has this tail as the comet is streaking through the sky or through space, and the tail is the result of it, leaving behind material. That's actually not true. Here you can see that the comet's following the elliptical path, and the tail's always pointing directly away from it. Well, the ion tail does. Okay, so Halley's Comet's worth mentioning because it has, in modern times, been a part of popular culture. It's got a period of 76 years from perihelion to perihelion. You can see some images on the left there from 1910 and then 1986 on the right. I can tell you, as someone who was excited about astronomy in 1986 and driving out to sort of darker areas to see it, I was definitely a little bit underwhelmed. It wasn't quite as big and bright as it was in 1910 in 1986. So the next time it comes around, it could have another big outburst and be big and bright in the sky. But eventually, as every time a comet gets close to the sun, it's going to lose a little bit of its material. So eventually a comet like Halley's Comet will run out of stuff, and it will have one last pass by the sun, and it will evaporate or disintegrate. So Halley's Comet, like many comets that come in close to the sun, are thought to come from the Oort cloud because of the angle at which their plane of orbit varies versus all the planets. So the point would be that there's this faraway cloud, maybe half a light year out, many AU out. There's this cloud of comets where the volatile stuff that the sun pushed away during its T-Tauri phase kind of stopped finally. And there's this, trillions or at least hundreds of billions or billions of comets, and they're just sort of hovering there, barely being held on by the sun's gravity. And when they bump each other, they end up with orbits that fall in towards the sun, and they're highly eccentric, and they are at a pretty steep angle relative to the plane of all the other planets' orbits. And that's one indication that this object came from further out than, say, the Kuiper belt. The Kuiper belt would be the group of cometary objects that kind of starts at Neptune. Pluto is considered the closest in Kuiper belt object. And it extends out pretty far, but not nearly as far as the Oort cloud. There are other reasons for comets to end up with highly tilted orbits. It doesn't necessarily mean that they came from the Oort cloud, but that's just one kind of leading theory. The cometary object itself is, like a mountain of ice, a big mountain of ice. So in the case of Halley's Comet that we mentioned a moment ago, it may have 10 to the 20th worth of kilograms to start with, and every time it passes by, it's losing material. I mentioned during the bit about meteor showers that Halley's Comet left behind a cloud of stuff that crosses the Earth's orbit, and every year we pass through it, and that causes a meteor shower. So you will eventually have a period where the comet breaks up, like this comet that was discovered by the Linear mission, the Linear, I think it was a survey, LINEAR, and you can see from the series of images that eventually this comet broke up. It got so close to the sun that it just broke into pieces. Some comets' orbits are so eccentric that they essentially, graze the sun, and they have fewer trips before they are disintegrated. Some of them even end up in the sun. It's one of the ways in which the sun acts to protect the inner planets and keep life on Earth safe from cometary impacts, because the sun has most of the gravity. Jupiter also has a lot of gravity, and has in the past, in the fact 1990s, it actually helped capture its own comet. So here is Wild 2 on the far left, and there was a mission to fly through the cometary tail called the Stardust mission. You can see the center image, the hand model there, holding what is known as aerogel, which you can actually now buy on the internet, which I think is strange. And it's very light, but it can stop the stream of particles flowing away from the comet. So the spacecraft actually flew through the tail, and we picked up cometary dust particles, and we're able to confirm how much water it has, and how much hydrogen and carbon and silicates and things like that. And it matched what we found for other solar system objects, but obviously comets are more water, more ice than they are rock. By the way, they are covered with regolith. So much like the moon and Mercury and asteroids, they are covered with regolith. There's dust that's piled up on them over their paths around their times around the sun. It's not the same as that's why they're gray. It's not the same kind of material, but it's similar. It's a really similar kind of sort of dusty material. The Deep Impact mission actually flew up to Tempel 1 and created a temporary tail, which is super cool that we did that, and saw how pieces of material were thrown out into space. So it was a pretty cool mission. It's one of those things that I'm sure sitting around some table at NASA making plans, and they're like, let's slam something into a comet, and they were all like, oh, we're going to do that. So it was a pretty cool idea. Several missions actually have had similar kind of general profiles, and it probably won't be the last time that we use an impactor to create a temporary sort of field of debris to study. Now I mentioned the Kuiper belt and the Oort cloud. Here you can see the two of them kind of put together. The Oort cloud is random. The cometary orbits can go in any direction. It's three-dimensional, and this 50,000 AU range, by the way, is totally like a guess. We're not exactly sure that that's the right answer. But the Kuiper belt is definitely planar, so it's flat instead of 3D. It's much closer into the planets that we would think of as the outer edge of the outer solar system, I guess, as Neptune's orbit, and that's also where Pluto's located, essentially, especially on this scale of 50 AU. So Pluto is just outside the orbit of Neptune. In fact, it's gravitationally kind of bound to Neptune, but we consider the inner part of the Kuiper belt as where Pluto is. It's also fair to say that the icy objects in the Kuiper belt count as cometary objects as well. So it's not just the Oort cloud, but there's also the Kuiper belt. But like I said before, most cometary orbits are so sort of angled. They're coming in at these very steep angles that it makes the most sense that they probably originated somewhere in the Oort cloud. So the most important comet to discuss is the one that the Rosetta mission looked at up close, Comet 67P, which has also a Russian name, Churyumov-Gerasimenko. And 67P was studied not only up close and personal by the spacecraft that orbited it, it landed a lander on it called Philae, and we were able to get very detailed up-close pictures and study the material. And I want you to notice there are not a lot of craters on this thing, because every time it gets close to the sun, it actually completely changes its surface. Some areas kind of crack open and jets of ice shoot out. Some areas are carved from some processes on the inside or on the outside. But it looks like Comet 67P is a pretty common sort of contact object. So two different cometary objects barely bumped into each other, sort of developed this bridge of ice where the contact force caused some melting, and then they kind of stuck together. And now we see that this is a common sort of outcome for comets. I thought that this was super weird at the time, but now as we've looked at other cometary objects, other icy objects in the Kuiper belt, for example, this isn't all that weird. At any rate, one of the interesting takeaways from Rosetta is that up until 67P's study, the idea was that most Earth water was coming from comets, but the water here had the spectral makeup of this object indicated, the isotopic analysis, I guess, would be a better way, indicated that it's not the same water. So it's an unanswered question about how much water that Earth has was delivered by comets and asteroids. It's definitely not a settled debate, but the Rosetta mission certainly kind of muddied the water, so to speak. Oh, that was a good pun. Man, that was a good pun, y'all. So, yeah, that's good. I'm going to leave the dwarf planet discussion for another day. Comets are underexplored, y'all, so one day when you guys go to space and you go visit them, you can name a crater after me. All right, thanks.